Hi everyone, and welcome back to this channel. In this video, I just wanted to go over Lab 3 for EE504. So it's the software-defined radio. In this lab, we're going to be making a BPSK and QPSK transmission system. So on the left here, I've got some random integer generators. And so you can pull up any of these blocks by just clicking on your canvas here and searching, the name of the block that's in there. So I've got a couple of random integer generators on the left here. And for the BPSK system, so in binary phase shift keying, you have two symbols, which means that your symbol or your set size here is set to 2. And so what that does is it generates random numbers between 0 and 1, right? So you're set at 0 and 1. And so I've got my sample time set here at 1 microsecond, which means that every second, it's generating a million samples. And then I've got one sample per frame. I'm going to change that to 1,000. And that just means that it sends out 1,000 of these samples at a time. And so here I'm passing the random integers into the BPSK modulator. And I'm also tying a stream of integers to my transmit error rate calculator. So this error rate calculator is comparing the transmitted integer with the received integer. Right, so you're going to want to tap the lines, before the modulator and after the demodulator. You can kind of see that in here, right? So after this modulator, at the complex signal, you can't really get an error rate from uh, looking at two complex signals. You want to look at the integers rather. So then I'm passing the modulated signal through my AWGN channel. And then in this channel, right, to get the variance, there's a little drop down here, and there's an option for variance, right? There's by default it goes to signal to noise ratio, and of course you can play around with that as well. For this experiment, we're just looking at the noise variance. We hit OK there. I don't think I needed to change anything in this. But one thing to note is that you can change the phase offset. So by default, this is putting out symbol. You can even look at it here. So this is kind of like our reference constellation. It's at an offset of 0, which just means that our first symbol is appearing here, right, on the real plane here. And then our second symbol is appearing up here. Sorry, I don't look quite right. There it is. So our first symbol is appearing here, right? So that's going to be tied to 0. It's appearing at 1, 0. And then our symbol 1, for 1 is a minus 1, 0. So if you were to change the phase offset to maybe 2, so it's going to be shifted 90 degrees. So I just go ahead and apply this and Constellation. And then you should see shifted 90 degrees, right? So the whole constellation rotates 90 degrees about this origin here. So that's just something to keep in mind. You have control of this phase offset. And when you're demodulating, you want to make sure that you have the same phase offset on either side. Otherwise, you'll be spinning up around constellation there for the wrong integer. And it's demodulator rather. So if we go ahead and open up, Constellation. Actually, first, real quick, just looking at the QPSK side, the only main thing that you would need to change for QPSK is that you have to go to your set size and change that to 4. You could have a set size of 2 at a point. You don't really need QPSK necessarily. And so if we open this up, we can run it. And so I've got my stop time set to infinite up here, so it'll just be free running once it starts going there. Here are the two constellations. Right in blue is the BPSK, samples after that AWGN channel. So if you zoom in, you can kind of see before the channel, and before the channel, the symbols are mapped perfectly because there's no noise. But if we zoom out here, these are 1,000 samples at a time, and you can see if we go back to my model here and I update my noise, say 1, of a variance of 1, and you can see now, the samples are much more spread out. And so if I bring this back down, 0.01, and you can just look at the error rate, right? So the error rate, when I change that back down to 0.01, is now going down, continuously comparing these integers over time. And as you can see, the number of errors, the number of values that it's compared is going up. And, just looking at the constellation, you can see that our samples are appearing very close to the uh, the reference constellation here. And so each sample, right, is going to be mapped to whatever symbol that it's closest to. That's kind of how the C modulator determines which integer is incoming. And so then you compare the transmitted integer, right? So this is what we want, that received integer, what's effectively being decoded by this modulator. And so I think that's all I wanted to talk about for the Simulink model. So the other part of this experiment was looking at MATLAB script. GitHub page there. So we just go to GitHub. Right, so out here on the GitHub page, we have Lab 3 from 2 years ago now, and it had, a modulation schemes for M, where it's just comparing pulse amplitude modulation with quadrature amplitude modulation, and I think QPSK. And so these are all, your symbol set is 4 in our main use cases, where for modulation schemes. So just going over what 4PAM is. So pulse amplitude modulation in general, your modulate or each symbol is going to appear somewhere along the real axis here, right? So you have something maybe here, right? So the in phase axis, maybe you have a 0 here, you have 1 there, 2, 3. It doesn't really matter. It's pretty arbitrary where you place your symbols. But just in general, this is what a pulse amplitude modulation reference installation would look like. So then going to quadrature amplitude modulation, so that's QAM, where our reference is going to be some combination of quadrature components, right? So we have in phase component and the quadrature component. So you could have, 1, 1, you could have a, here, there's -1, 1, -1, -1, 1, -1. That's just an example of QAM. And then for, I don't really want to write QPSK. I'm going to write the more general PSK. It's phase shift keying. And in phase shift keying, we are mapping our symbols kind of along the unit circle. I guess not necessarily the unit circle, but what's happening is you're adjusting the phase angle at which your constellations here, right? So if you have somewhere here and here, and so this is the case for BPSK, right? So that's for a two binary signal, call it two array. For 4PSK, you could have two more symbols appearing here and here, and you could rotate this constellation around the unit circle to just introduce more phase shift. And so some were asking what's the difference between uh, like QAM and 4PSK, QPSK rather. And so the main difference is that, while it would look the same, the fundamental signal vectors that go into creating this reference constellation are slightly different. Uh, that's just one thing to note when going through this, because I know we didn't talk much about QPSK or QAM and PAM, in the experiment. So I just wanted to go over that briefly. The other ones, so these loopback.m files, I forgot to put in a reference for this, so I sent out an announcement. So the loopback.m and I want to say the loopback16 qam.m. So these are both coming from this book, Software Defined Radio for Engineers. And so I think this is a really good reference, for learning about radio concepts and Pluto, how to use Pluto in general. I'm yet to go through the whole thing. So that question about how hack, I think if you just look up how in here, you might get some results. Yes, it's coming from this chapter 6 on timing synchronization. But you can just see what kind of explanation that they have regarding this. And I believe the other one is also in here, that 16 QAM. So I think that's all I wanted to go over. Sorry I didn't get to put this video up for the lab session. Thanks for tuning in and see you guys next time.